This is the demo video for the binary bandits, and today we'll be showcasing our 4-bit arithmetic logic unit. Starting off, we will be doing our AND logic unit. Here we have mapped inputs A's and input B arrayed across switches 9 through 6 and 5 through 2 respectively, and our opcode is using switch 1 and switch 0 as well as key 3 and key 2. For the first, we have a simple bitwise AND implementation. For the test case, as you can see, with both zeros, 0 is passed straight through. With 1 on one switch, you'll obviously nothing pass straight through. Only once it's activated on both switches is it actually passed through. So if I take one off of either side, disappears. So 1 0 1 0, for example, will only 1 0 and then 0 1 1. As you see, only the ones that are active on A are passed through, showcasing the bitwise AND functionality. Now, moving on to our next opcode, down to the OR logic unit. With 0, it only takes 1 on either side to pass it through, while holding down this to activate the 0001 opcode. As you can see, it only takes 1 on either side. Both can be activated, it has no effect, since it is bitwise OR. See, we can do any combination to effectively combine these. Now, showcasing our next logic unit, XOR bitwise, on the opcode 0010 by holding down key 3. Having one input active shows that input, but as soon as we add it, wrong switch, as soon as we add it, it nullifies out. As shown here. Now, moving on to our bitwise inverter. On the opcode 0011. So holding down both keys. As you can see, all of our inputs have already been inverted, showcasing F on what should be just 0. As you can see, all our inputs are inverted on the A array, or A vector. And B has been blocked out since we're only operating on 4 bits, not 8. See, since we're operating off of the assumption of 15, you subtract 8 from there, you get to 7, and so on and so forth. Just a simple bitwise inversion. Now, to our full adder. We have a full adder implementation on opcode 0100 using switch 0. Now, we have implemented a full ripple carry adder that includes a carry in and a carry out functionality. Carry out might be hard to see since it's under the sticker. It is this LED right by my thumb next to the sticker here. I'll try to tilt it if necessary to show it. Now, on the adder, we have inputs A and B, and opcode is already in, and our carry in is bound to key 1, as shown. Now, for example, if we 8 with that carry in, that will be 9. Now, if we do 8 and 8, it will overflow because 8 plus 8 will overflow the hex and it will go to our carry out as shown here. But you can add on top of that as well. So we can add these 4 bits, or we can add the binary 4 together to get 8 as well as our carry out. or any other combination we so choose. Or if we want to ride just the edge to show the carryout functionality, you can just do this, and then as you can see, when we overflow it by pressing down our carry in, we get our carry out respectively. Now moving on to our comparator. Oh, thanks for pointing that out. Anyways, moving on to our comparator on the operation code 0101. So with switch 0 on and key to depressed. Now, inputs A and B. When they are equal, you will see E for even, and if A is greater than input B, then the respective letter will be shown. For input A, since A is greater, A is shown. Since B is greater, B is shown. You can do this for any combination. It is not bitwise, it is full across the combined array. Nope, I almost changed my opcode by accident earlier. You can see when B is greater by any amount, B is shown on the hexadecimal display. And likewise with A, and when they're even, E is displayed self-explanatorily. And for the rest of the section, my partner will be taken over to demonstrate our is odd and is even functionality, as well as our sequential functions.
Okay. Taking over for is odd, it only uses the A 4-bit inputs and still uses the same opcode. So for this opcode, it'd be 0110. Which is instantly working. So pretty much whenever the least significant bit, if that is 0, that means the whole thing is even. So right now, since it's not on, as you can see here, then it'd be odd, because as this is 1, 2, 4, and 8, so no matter whether or not these other 3 switches, so if it's 1, 1, 0, 1, it's going to be odd because this least significant bit is 1, which makes it odd. Compare it, and if we do 1000, it's going to output false because it's 8 in decimal. And also for 1011, it also give you odd because this least significant bit, which is 1, is currently active. Moving on to the is even. Oh.
Keep going.
Yeah, I'm just making sure it's mapped. I can see it on the camera.
Alright, I'll try to keep an eye on that for you.
Yeah.
Just make sure to move the touchpad every once in a while so it doesn't fall asleep.
For is even, essentially the same, but it's checking whether or not the value is even. So it outputs a E right here. It's outputting an E because 0 is an even number. And also we have 1011. It's going to output F because the least significant bit is 1, which makes it an odd number. We also have 111, which is even because this would be 8 plus 4 plus 2, which is an even number. Okay. Moving on to the sequential part of our designs. You can see it up here first. We have the Pipo shift right, which is using a clock that is 50 megahertz that goes into a clock divider that is outputting at 2 hertz, so it allows us to see our actual display here in the hex without it going like insanely quick, so we can actually see what we're outputting. So with the hex code for the shift right, it'd just be 8. And then we also have, we're still using our A inputs, and for the B vector that we aren't using, we're using B3 as the load shift and B1 as the push value, that it's either a 0 or 1. We also have a reset that's mapped to our key 0 that we're using. So for shift right, if we have 0101, and here we load it up, it gives us a 5 as of right now, and if we're pushing in a 0, the expected output should be a 2. So whenever I let this go, it should be 2, and then since it's pushing in a 0 from the right side, it's eventually going to 0 out. Moving into our next one, which is 1 0 1 1, we're going to put the load shift so you can actually see whenever it shifts. So right now it's A, and we're going to be pushing in another 0, which this should be giving us a 5 whenever I let this go. As you can see, and like I said, it zeroes out since it's pushing in a 0. And for our last one, I'll be showing for the shift right, it would be 0 1 1. We're also going to be pushing in a 1 this time. So whenever I let go of the load shift, with the expected output should be 1 0 1 1, which would be a B. And as you can see right there, it outputs a B. Since it's pushing in 1s from the right side, it's eventually gonna the 4-bit vector is going to be full of 1s, which is going to output F in hex. Moving on to our shift left, if you can see it on the up there pretty nicely. It's essentially the same as the shift right. Instead, we're shifting everything to the left. So we're pushing in the values from the left side, which is essentially timesing by 2, which we're using the same load shift, and we're pushing in 0 or 1. Have the same different opcode, and we also have the reset over here. So for shift left, if I'm doing 0 1 0 1 0 1, I'm loading that, and the opcode would be 1 0 0 1, which would be this, and here it's loading, and here's my reset whenever it does work. Well, oh shit. Oh, small mistake, I did not have the right opcode on. So it would be 1 0 0 1, and then here testing my reset, then it works, which is the shift left. So first, as I said, I'm going to be doing 0 1 0 1. I'm going to be loading that up, which would be 5, and we're also going to be pushing in a 0. So the expected output should be 1 0 1 0, which should be giving us A whenever I let this go. And that's exactly what it does. And since it's pushing in a 0 from the right side to the left, it's eventually going to 0 out. Moving to our next test case, whenever it's 1 0 1 0, we're going to load this so it's more easier to see. And we're also going to be pushing in a 0. And the expected output should be 0 1 0 0, which would be 4. So whenever I let this go, exactly what it does. And it pushes in a 0, so it's eventually going to 0 out. And for the last test case, 0 1 1 0, which will also be loading, but we will be pushing in a 1 this time. And that would be 1 1 0 1, which would be outputting a D, as you can see right there. And since it's pushing in a 1 from the right side, it's timesing everything by 2, which eventually is going to output an F, since everything, all the 4-bit vectors is going to be filled with 1s. Okay. Moving on to our PIPO bidirectional, which is pretty much shift left and shift right combined. And once you can see, instead for the B vector, we are also adding the direction. So whenever it's 0, it's shifting to the right, and if it's 1, it's shifting to the left. And we still have our reset. The opcode is going to be different. We have our load shift push value, and we're still only using the 8 input values. This opcode would be 1 0 1 0. And right now, since direction is 0, we're going to be shifting right. So we're going to be doing 1 0 0 1. Make sure everything is loading in. As you can see right there, it's a 9. Our direction is going to be 0, so it's going to be shifting to the right. And our push value is going to be a 1. So the expected output should be 1 1 0 0, which would be a C whenever I let this go. Exactly what it outputs. Moving on to another test case, 0 1 1. We're going to load that up, and then our direction is still going to be shifting to the right, and we're going to also be pushing in a 1 as well. So the expected output should be 1 0 0 1, which would be a 9. So whenever I let this go, it's like what it gives us, pushes in 1s from the left side because it's shifting right, so eventually it's going to go all the way to F. For our last test case for this bidirectional, it's going to be 0, 1, 0, 1, which we're also going to be loading so it's easier to see. And we're going to be shifting to the left. That's why we have the direction on. We're going to be pushing in a 0. So the expected output should be 1, 0, 1, 0, which would be A. So whenever I let this load shift go, it gives us A. And since it's pushing in zeros, it's eventually going to zero out. And that's it for our bidirectional. Moving into our last sequential component, which you can see it up here, which is our bidirectional counter starting at an input value. We're still using this only the 8 input 4-bit vector, and we're still using the direction, and essentially the load shift is the same as the preset, but I just mapped it to our last switch that we are currently not using, which would be switch 2. Our opcode is still the same. We also have a reset for this. So for the bidirectional counter, if we have 1, 1, well, the bidirectional counter, you can add 1 or subtract 1 depending on what direction you go. So if you have 0, you're subtracting, and if you go to 1, you're adding to the number. So if we have 1, 1, 0, 1, and our direction is 1, which means you're going to be adding by 1. Oh, no.
Preset.
My bad. The preset, we're going to have the preset, my fault, our test case is worse. It's kind of flipped around with the preset direction. So if our preset is 1, it should, and we have, well, first the opcode, my fault. It's 1, 0, 1, 1, so this should be 1, 0, 1, 1. It's the preset's going to load in our value C right here. And so then if we have our direction going 0, it's going to be subtracting. So whenever I let this go, it's going to be counting down. Well, counting up. Down, I mean. And then once it goes to 0, it also goes, well, that was going to be another test case, but whenever we have 1, 1, 1, 1, and it's loaded in for the preset, it's going to be F. And if direction is going up, so it's going to be adding, it should go to 0, which would be 0, 0, 0 from 1, 1, 1. And that's exactly what it does, as you can see. And the same thing for whenever we have all of our inputs as 0, and we want to go subtract, so our direction would go down.
Add. Well, because you want to start from 0 and then add.
0, so our direction is going 0, so we're subtracting. Once I let this go, it should go from 0 to F, which it's doing, and it's subtracting, which is exactly what we want. And then, just to show our reset works, if once we have our preset and we have it like this, and then our reset over here works as intended. And that concludes the end of our ALU. Thank you for watching.